We are live.
Okay, good morning, everyone, and thank you for joining the Canadian Underground Infrastructure Innovation Center Academy webinar for today, Pipeline Construction Planning with Geophysics. My name is Tamer Shimi. I'm a Principal Geotechnical Engineer with Thoroughbore Engineering in Edmonton, and I am the current chair of the CUIIC Geotechnical Subcommittee, and I will be the moderator for today's webinar. This webinar is organized by the Canadian Underground Infrastructure Innovation Center, CUIIC, the University of Alberta, and Benjamin Media. CUIIC Academy offers classes, courses, webinars, and events to help further underground infrastructure educational opportunities across Canada. The CUIIC Academy webinars happen every third Thursday of the month and cover a variety of pressing topics related to the underground infrastructure sector. Speakers include industry-leading professionals who will provide a monthly free educational webinar to the public, followed by a question and answer period. For a full list of upcoming and past webinars, please visit academy.cuiic.ca for more information. For CUIIC's in-person events, please save the date for the upcoming Pipeline Rehab Academy on March 5th and 6th, 2025. That will be in Mississauga, Ontario. Attendees will get the chance to learn about the most up-to-date advancements and new technologies available to repair and rehab the aging infrastructure. I'd like to thank our 2024 webinar series sponsor, Westlake Pipe and Fittings, for supporting underground infrastructure education and innovation. Now it's time to introduce our presenter for today's webinar. Max Slayton is a geophysicist at BGC Engineering in Edmonton, Alberta. He has been working for the last 11 years collecting, processing, and interpreting all sorts of near-surface geophysical surveys. His experience has been quite varied, from mapping bedrock and geohazards for pipeline and mines to groundwater exploration for industrial and humanitarian projects. He had worked on numerous pipeline construction projects throughout Western Canada and the US. So thanks again, Max, for your time today, and please take it away.
Thanks, Tamer. Hi, everybody. I'm here today to talk a little bit about how geophysics can be used to assist with pipeline planning and construction. Just as a disclaimer, we're mostly going to be talking about trenchless crossing examples, but these geophysical techniques that I'm going to talk about are mainly for mapping geology, so they can be applied to all sorts of problems in the pipeline construction process. So while there are several different trenchless crossing methods, a very common one is horizontal directional drilling, or HDDs. These are usually done on longer crossings where conventional trenching isn't an option. Say your pipeline's hitting a river or a wetland or some sort of sensitive area where you cannot trench. Basic principle behind HDDs is we get to the area, the obstacle, we drill a hole underneath, pull the pipe through, and we've crossed our obstacle. However, HDDs can be pretty risky to undertake because if things go wrong and the crossing fails, the costs associated with dealing with that failure can be huge. And then if there's any delays to the installation of the pipe and there's key deadlines that are missed, there can be even bigger costs associated with delays to the project itself. So to avoid this, you generally want to have a good plan for your HED, and the designers want to make sure they know what's underground and what they're likely to encounter. I'm sure there's many things to consider, but from my experience, some of the main questions are, where's the bedrock? What's it made of? Are there any weak layers within the ground that are going to possibly cause a slow failure? Is bedrock shallow enough or that I can drill into it, or is it too deep and that's not an option? But often, more importantly, are there any granular material zones, like coarse grain zones of sand or gravel or cobbles? These granular materials can cause huge problems. They're often discovered when the HDD is being executed, and it can either cause mud circulation issues, it can collapse the hole, it can chew through bits, it can damage the pipe coating when the pipe is pulled through. They can largely stop a drill in its tracks. And it's usually because people aren't prepared to deal with it properly when they encounter it. So let's start with a simple example. We have this river that we're looking to cross underneath. The team is evaluating the feasibility of doing an HDD here. We have an initial plan of where we think the bore path is going to go. But to figure out what's underground, we're generally going to want to drill a couple boreholes because we need more information than just lines on a map. We'll usually drill at least two, one near the entry, one near the exit. And from these, we can see that, we've hit bedrock on either side. So we can see that this orange sort of lens by the HDD entry on the left, there's a bit of a granular zone. We'll call that orange bit granular. Maybe it's not a problem. It's shallow. We can case through that, and our bore path continues on, and bedrock looks to be a similar elevation on either side. So perhaps it just goes straight through. And I mean, looks like not so bad at this point in time. But what if it looks like this? As of right now, we can see there's a depression in the bedrock. Scour, maybe not so hard to imagine with a river channel. There's more granular deposits underneath the river. And as it stands right now, the bore path is going through one of these orange zones. We'll call that a granular material, and that's nearby the exit. That could cause huge problems for us. And if we don't know about it beforehand, and we find that out when the drill was going through, it could cause multiple days of delays for the project. Maybe if we knew about this information before we drilled the geotechnical boreholes, we could move our geotechnical boreholes or add one and intersect some of these questionable zones. Or maybe we know that there's these granular layers and we want to move the entry and the exit, and that means we want to move the two boreholes that we've drilled. We want to move them into a different spot. So moving any of these or adding extra boreholes, these have big implications on risk and cost, and it would be good to know this information before we're undertaking this construction process. So enter geophysics. Geophysics surveys, they offer non-intrusive methods for imaging the ground and helping answer some of these questions. I'm going to go over a few examples over the next couple slides, but in general, they allow us to measure the physical properties of the Earth and make some interpretations about what materials we're likely to encounter either when we drill the HDD or drill some of the geotech boreholes. For the most part, we can conduct them on foot. We can put them across streams, down steep, rugged slopes. They can provide continuous information on these rough terrain areas that are possibly not accessible to drill rigs. And by incorporating geophysical surveys into the planning stage of the project, it's very useful for augmenting information that we already have from boreholes or helping us figure out what kind of information we want to look for with additional boreholes to make informed decisions when we're planning the construction of a pipeline. So the first example I'll talk about is seismic refraction. Seismic refraction tomography, or SRT, is it's an excellent way for imaging bedrock. Some of you may have heard of it. It's similar to seismic surveys for an oil and gas exploration survey. And where these differ is that these oil and gas surveys are focusing on imaging deep into the crust, maybe not super deep, but hundreds to thousands of meters. And they're optimized for imaging deeper, whereas these shallow seismic refraction surveys are optimized for shallow engineering problems. And how they work is I have a person with a sledgehammer or a person with a small explosive, and they generate acoustic waves in the earth. They propagate through the earth, traveling up and down a string of geophones that we've laid out. Geophones are just simply very sensitive microphones that measure vibrations. As these waves travel through the earth, we know the position of the sensor, we know the position of the source, we time how long it takes for the waves to propagate, and through some simple math, we can calculate the velocity that these waves were traveling. Now, why do we care about this velocity? Well, this acoustic wave velocity, or in particular the P wave velocity, is directly related to how dense a material is, how compressible a material is, what are some of its mechanical properties. They travel fast through dense, rigid, incompressible materials, and they will travel slower through more loose, unconsolidated, less rigid materials. So put simply, fast P wave velocity means rigid material or bedrock. Now, this is an output of an SRT survey. This is what you're likely to get when you conduct one of these. This was collected on a pipeline project that we've worked on in the past. And this is what you're looking at here is a velocity cross-section. The pink colors are fast velocities. The blue and green colors are slow velocities. So pink is dense, rigid, incompressible rock material, and the blue and greens are the unconsolidated overburden. And in this example, we can see that there's blue in these stick logs. The blue is clay. Those hatched materials, it might be hard to see the hatching on the bottom, is bedrock, and we've scaled it so that the pink is indicating bedrock. And we get a nice continuous profile from following along this velocity contour to see the bedrock profile underneath the river going across where this pipe is. Second technique I'll talk about here is called electrical resistivity tomography, or ERT. We mostly call it ERT because electrical resistivity tomography is a mouthful. And it's very simple. It works similar to voltmeters that you may have used in the past. What we're doing is we hammer in electrodes into the ground. These electrodes are just stainless steel rods. We create an electric field by applying a voltage between them. And using another pair of electrodes, we're measuring the voltage or potential difference in different areas within this electrical field. And through some, again, simple calculations, we can collect the we can calculate the electrical resistivity of a material. Now, in practice, what we do is we lay out a cable with many different electrical takeouts, and we hammer in many different electrodes into the ground and connect all these to a central computer, which then picks different pairs of electrodes to survey. And it just so happens that if you put your electrodes close together, it samples shallow. If you put them further apart, it samples deeper. We conduct 1,000+ measurements of these different surveys, and we can calculate another cross-section. This is the output of an ERT survey. Again, pink values are high, blue values are low. Pink values are high resistivity. Most of the time, high resistivity values are related to coarse-grained materials, and low resistivity values are fine-grained materials like clay. And you can see the borehole on the right. We see coarse-grained materials in the near surface, a thin layer of clay, which matches up nicely with a low resistivity layer, and that is underlain by sand or silty sand in the borehole. And we can see a clay layer in borehole 1 at the bottom that's sort of extending into the ERT. But what we don't see in the boreholes is this clay layer in the middle and the sand/silty sand lens on the bottom, and this thin zone of high resistivity that we're interpreting as sand and silty sand coming across the middle. With this, using the ERT in conjunction with the boreholes and with previous knowledge of the site, we can make some pretty informed decisions and make a continuous profile of interpretations in between these boreholes. Both ERT and seismic surveys can be collected in the matter of days. This particular survey is 100 meters long. It was going up a slope. It can be collected in a day easily. That first seismic profile that you saw was 700 meters long. It can be collected a day, day and a half, depending on the resolution required for this particular survey. Often, we would recommend collecting them at the same time. Top, we have an ERT profile. Bottom, we have a seismic profile. And the reason why we say we want to collect both at the same time is because they give us different information. The seismic survey tells us more about the mechanical properties, i.e. how rigid, dense material may be. But it's not so, it turns out that gravel and sand and clay all have a pretty similar level of compaction and strength, at least in terms of the P wave velocity. So gravel layers and sand layers aren't as apparent on seismic, whereas they will have quite a bit different electrical properties. So by doing them together, we can map out these coarse grain layers with the ERT, show where they are above the bedrock. So we've picked bedrock from the seismic. We put that on. You can see the white dashed line on the top is the bedrock interpretations from the seismic. And we can see that there's some high resistivity zones above the bedrock that are likely gravel or sand dominated layers. Now, sometimes these surveys, while we can connect or collect them across streams, sometimes the river itself is too wide for us to actually lay the cable across. So here's an example. This is the North Saskatchewan River. We collected a survey for a pipeline HD plan just outside of Edmonton. And what we can do is do land-based ERT and seismic on either side of the river and a waterborne ERT and seismic survey on the river itself. And the waterborne ERT, waterborne seismic, they work basically the same way. They, except instead of planting the geophones and electrodes into the ground, we have a streamer with electrodes and geophones connected with or integrated in a cable that we tow behind a boat. This boat drives up and down the river or stream and collects a continuous profile that's perpendicular to the crossing of the pipe, which you could collect it along the pipe. It's just with the river flow, it doesn't quite work so well. So it's best to get many lines up and down the river. And an example output of that is ERT and seismic on either side combined with waterborne on the river, what we see here. The dashed black line is the proposed HDD path. This is just northeast of Edmonton, nearby Fort Saskatchewan. The dashed red line is the interpreted bedrock from the seismic. And you can see these slices underneath the river. Those are the seismic and ERT profiles that were collected and extracted at the particular HDD path. And from these, we can glean quite a bit of information. We see coarse grain deposits above bedrock. There's these bright pink deposits nearby the entry and exit point. There's bright pink on the slope, likely colluvium. Those are all interpreted as coarse grain materials. On the right side of the crossing or east side of this crossing, we can see those orange, yellow zones in between the two boreholes. Those are likely coarse grain materials again, and they're very close to the proposed HDD path. So this might be information that we want to know before we start drilling. Underneath the river, we can see increased resistivity layers in the waterborne, but those might be less of a problem because HD is way underneath it. In the seismic, the waterborne seismic is excellent for picking the bedrock here. It shows very clearly where bedrock is underneath the river. On the right side of the crossing, this zone that I've highlighted as possibly weak bedrock, we know that's bedrock from the borehole that's right next to it. But the seismic, the P wave velocities are quite slow in this area, which may indicate that these are possibly weaker areas that it might have geotechnical considerations for potential slope failure. One final thing that we can, not final thing, another thing we can do in on these pipeline projects that's not necessarily HDD, but is quite helpful, is mapping organics layers. Often organics layers are mapped by test pitting, just going along with a backhoe and digging to see how thick it is. But these surveys are ground penetrating radar surveys. It works very similarly to seismic. Instead of the only difference or main difference is instead of sound traveling through the ground, it's radar waves traveling through the ground. And when these radar waves go through the peat and hit the mineral soil underneath, they will get reflected back up to the surface. And some of you may have seen these push cart type radar antennae on the bottom left, but you may not have seen the more rugged radar antennas. It's like towing a garden hose, and you effectively can walk through most material. They're very rugged, and this survey here is a couple hundred meters long, and it takes as long as it takes to walk a couple hundred meters. So it's very fast, and the bottom of the organics layer shows up very clearly on these particular radar surveys because it's such a big difference in material between the peat and the mineral soil to the radar wave. So we can get a continuous profile of how thick the organics are all the way along this pipeline alignment, which may be helpful for buoyancy control or material volume calculations and whatnot. A couple more techniques that I will mention that I won't spend too much time on these. The TTEM or towed transient electromagnetic survey is very similar to ERT. It's in some ways better than ERT. It's mobile. You can tow it around wherever you go. Where ERT, you need wider cables to see deeper. For the TTEM, it's contained and you can look deep within this tight little package. The main reason why I didn't spend the time talking about TTEM versus ERT is you need a 2 to 3 meter wide at least cut line to pull this through because it is quite large, and it's quite sensitive to metal. So if there's already pipe or metallic infrastructure nearby, and by nearby I mean say within 50 to 100 meters, or power lines, it can impact the results. So it's great for greenfield type applications, but if there's infrastructure, it's maybe not the best option. HVSR is another very quick, cheap method to deploy. You plant a seismograph in the ground and you measure the shaking of the ground. It's a different seismic technique, and from that you can get the shear strength or shear properties of material. You can calculate bedrock depth. The drawback to this one is you do need intrusive information to calibrate the results properly, specific shear wave, or specifically shear wave or bedrock depth in order to get that. But if you have that information, it's very quick as a reconnaissance tool to go around and check certain areas. Then there's some downhole methods, either downhole seismic profiling or crosshole seismic methods. These are particularly useful if you have boreholes and you want to know shear strength and material within the boreholes, or if you have boreholes and you suspect there's voids in between them, you can do crosshole seismic or crosshole ERT to map these voids. Again, useful. You just need to make sure that you have either some sort of instrumentation or a hole that you can stick the instruments down. So in summary, geophysical surveys can be quite useful for providing quite a bit more information than just singular boreholes. They should be used in conjunction with boreholes. I'm not suggesting that they replaced drilling boreholes. It's just an excellent thing to add on next to boreholes. We can interpolate things between layers that we see. We can possibly identify zones that were missed by boreholes. Ideally, these profiles can go all the way across the river or through the zone of interest. But if we need to break the line, and because there's a wide river, there are waterborne techniques that we can use to fill in the gaps in between. And depending on what you're looking for, there's many different applications. I only talked about a handful. but there's likely, if you can measure it in the ground, it's like there's likely a geophysics survey that is able to provide a map of where that particular zone of interest is. So with that, thank you all for your time. And if you have any questions, I'm happy to answer them. Again, my name is Max. I've been doing this for a long time, so I'll endeavor my best to answer whatever questions you may have.
Perfect. Thank you so much, Max, for the presentation and the good information there. It looks like we have already a few questions here. First question is how far away the borehole should be from the drill path? Asking because if borehole is too close, it could be itself become a frack out risk.
So this actually might be a better question for you, Tamer. I don't drill the boreholes too often, but in terms of like how far do you need the borehole away from the geophysics to help the interpretation? That's more dependent on how quickly you're expecting the lithology to change laterally. I mean, if we can easily, if the borehole is 10, 20, 50 meters away, we can sort of extend, especially in Western Canadian Sedimentary Basin. It might be similar. However, if there's small sand and gravel pockets, you might miss those. So you can possibly chime in on the frack out risk.
No, you're right. And it has to be off the alignment of the pipeline, enough distance to make sure that the risk of frack out is minimum. So thanks for your answer. Second question is, how does the water table affect the results of an SRT survey?
So the water table is like, if you're looking to measure where the water is, seismic refraction is probably not the method that you would want to use. Like ERT is sensitive to water content. Dry materials conduct electricity, they don't conduct electricity at all. You can, if you take a dry sponge and try to put it in an electrical circuit, it's not going to do anything. But if you add a bit of salt water to it, it will conduct electricity. So ERT is much better suited for mapping the water table. Seismic, in practice, you may be able to see it, but in practice, it's not the way to image the water table. I would suggest using more electrical methods which are sensitive to where the water content is in the ground.
Okay, perfect. What are the limits of geophysical investigation, i.e. depth and range?
So that's a broad question. It depends on what you're looking for. So depth, practically speaking, there is no depth, but the trade-off for all of these techniques is the deeper that you want to see, the lower the resolution is. So if you're looking at imaging 60, just to provide concrete numbers, say your target is 50 meters underground, that can easily be measured with ERT and or seismic. Your resolution is going to be of the order of a couple meters in that area. But if your target is 500 meters underground, you're now, yes, able to map it, but it needs to be thick enough and big enough of a target in order to be able to be seen. So the limits are different for all the different techniques, basically, to answer that question. Without knowing specifically the technique you're wondering about, it's hard to do, but we can largely tune the parameters of the surveys to account for depth and resolution goals for the particular surveys.
Max, can you comment on the same question for GPR?
Yeah, GPR is highly dependent on the conductivity of the ground. So GPR itself, muskeg, you can map quite thick muskeg. So if you have 2 meters of muskeg and it's underlain by clay, you'll see that likely. It depends on the antenna frequency that you use. But if there's a lot of clay, it doesn't penetrate through the clay very well. So if you have clay zones in the near surface, you can't really see underneath them. So radar, we're kind of talking depth or resolution is very good, of the order of a couple centimeters. Depth, anywhere from a couple centimeters to a couple meters, maybe up to 5 to 10 meters if the conditions are perfect. But often you're looking to map things shallower than that or thinner than that. But if you get to an area where you have really poor depth of penetration, that means you likely don't have muskeg. So if you're just trying to do it for muskeg mapping and you get to a bit where it's not going into the ground, you've kind of answered your question there of, well, it would be going into the muskeg. So it's not going in and I'm walking on clay, no muskeg. Typically you don't find muskeg underneath the clay.
Okay, thank you. We have lots of questions, Max. Can a waterborne type ERT or SRT be also done in muskeg areas?
Waterborne, no, but maybe if it's like muskeg and pond, yeah, sure, you can do that kind of thing. You can do land-based seismic and ERT in both of these areas. There are swamp geophones, we call them, and they're waterproof, and you kind of shove them into the muskeg. And ERT works fantastically in muskeg, wet muskeg. And if it's dry, you can just peel it out of the way and hammer the electrode in underneath it. But yeah, ERT and seismic can certainly be done in muskeg areas. Whether or not you want waterborne depends on how much water there is. Typically, we do land-based surveys in these areas anyways.
Okay, thank you. I think you already answered this question. What is the maximum depth capability of land and waterborne ERT and SRT? I think you already answered that one.
Yeah, I mean, just broadly speaking, for pipeline applications, their pipes they often aren't going too deep for ERT and seismic surveys to image.
Another question here, I found the ranges of electrical resistivity values for the same soils are generally different for investigation. What is the reason?
Yeah, for that, I might need more specifics. You're welcome to shoot me an email if you're wanting to talk about that. Just to take a wild stab, it could have to do with moisture content. It could have to do with maybe there's different geochemistry involved within these soils. Perhaps it's the same material, but there's different dissolved ion content in the two areas. We use ERT I've done it for years, mapping out contamination plumes for oil and gas related operations. If you have produced water spills, these dissolved ions will go into the ground and you can map out these plumes. So it's not necessarily lithology that's controlling the electrical properties. Often it's chemistry as well.
Okay, sounds good. It looks like we have like 25 questions or something now. The borehole casing will not affect the survey?
Likely not. Maybe, but if you need me to be right on top of it and you want an electrical method, the casing's metal, that provides like a electrical pathway which can influence things. But if you're able to step off either side a couple meters, you can it's not affecting it. It won't affect seismic. And yeah, if there's many questions, my email's there. If you want to send me questions, we run out of time. I don't know when we're going to run out of time. I have time, but you're welcome to send me emails.
We still have time. There are some very good questions here, actually. So let's take a few more questions. There's a question here. What geophysical method would you recommend for mapping a deep wood sawdust organic layer about 20 meters deep within a river overlaying bedrock?
Interesting. I mean, if you're looking to map organics on top of bedrock, both ERT and seismic would work for this. The bedrock itself is going to be fast and rigid. The organics are going to be really slow. So there is quite a bit of a contrast. The ERT should also be able to tell the difference between these. Possibly there's other EM methods that could work. I see the next question. What is P wave? What does P mean? Primary. It's sort of a convention that the physicists made a while back. It's basically a compressional wave. So if you imagine a fireman's line of people passing buckets to each other, the way the buckets travel through, that is sort of a P wave type thing. It's not hugely important what the P means in that case.
Okay. There's a good question here from Kelly. with seismic refraction, is it possible to mistake the elevation of the water table for a transition to a dense layer?
Yeah, like you can, and that's often why you want to do both ERT and seismic. But like the velocity of sound you might see a change in velocity, but the velocity of sound in water is about 1,000 meters per second, but the velocity of sound in rock is over 2,000 meters per second. So you're likely going to look at this velocity layer and still think it's overburden. If you see any water velocity related things, it's too slow. Put simply, too slow to be bedrock.
Okay.
And frozen soils, I see this one. Yes, they react differently. Seismic is it works in frozen soils, but yeah, they will react differently. Like ice conducts electricity differently. Ice has faster sound velocities than unconsolidated materials, but usually you can account for this when you're making interpretations.
Okay, one question. Would you see a benefit to using geophysical survey or techniques in environmental borehole drilling?
100%. 100%. You can do like environment if you're looking for contamination. There's maybe not necessarily seismic. You could want to do seismic, but there's a lot of other quick techniques. EM or electromagnetic methods are a way of like rapidly mapping out contamination. These techniques can show sand layers that are possible receptors. There's downhole geophysical techniques that are, we talked about downhole seismic and that kind of thing, but there's also downhole electrical methods, which give you much better vertical resolution of the electrical method or electrical properties of the material. So if you do have like contaminated layers, you can map out specifically like where they are underground with these downhole methods, and you have holes into them.
Okay. There are a few other questions about the depth that we already touched on before. Can you use ERT or seismic geophysical methods to identify voids around buried infrastructure?
Oh yeah, totally. You can, it depends on the size of the void. Like if you're thinking pinhole voids, honestly, probably not. If you're thinking of massive voids that are maybe associated with washouts, yeah, you can see these kinds of voids, mainly because the electrical properties of these voids, air doesn't conduct electricity very well, but the surrounding material does. And air has a much slower sound velocity than the rock or overburden, so you can see those kinds of things. There was a previous question, without borehole information, can you differentiate bedrock from overburden? You can with seismic. It's best to do both because it's great to calibrate in between. ERT, you can also make a guess as to where bedrock is, but if you have no information, sand versus clay or sand versus mudstone may have like a similar look in an ERT cross-section. But with seismic, if it's fast enough, it's almost certainly rock.
Right. Okay. Can you touch on the spacing required for the ERT if you're going deep or versus you're going shallow investigation?
Yeah. So if we have a 1 meter spacing, we can resolve features that are about 1 meter thick with a depth down to 30 to 40 meters. Most of that resolution is going to come shallower. If I have a spacing that's, say, 20 meters apart, you're looking down 250, 300 meters, but you need to be measuring blocks. The blocks need to be 20-ish meters thick. So we've done these types of surveys, these large spacing surveys to map out oil sand layers because they're deep and thick and very resistive. So if you want a rule of thumb, think like about 12 to 15 times the electrode spacing is the depth of investigation that you're going to get. And you can do whatever electrode spacing you want. In practice, it's not quite that simple, but we don't need to get into the specifics of why it's not quite that simple. But largely speaking, 1 meter, about I don't know, 20-ish meters. I know I said 12 to 15, but it's not quite that simple. And then 20 meters, you get a couple hundred meters deep.
Okay. How does a road affect an SRT survey?
Road, like, there's a couple ways of handling it. Largely, you're not going to see it in the cross section itself. The way that it impacts it is you can't. The standard geophone is a spike that you shove into the ground. We do have they're called streamer plates, where it's like a heavy plate that sticks on the road, and rather than the spike coupling the geophone to the ground, there's sort of a heavy plate that couples the geophone to the ground. Or you can drill a hole into the road if you're willing to put holes in the road and stick the spike into that. Or you can just skip geophones if the road is narrow enough and you don't put geophones across the road. Oftentimes, it's not going to ruin your results. You'll be able to interpolate around it or interpret things that are happening around it.
There's a quick question from Justin here. Is this method applicable for mini or mid-size HDDs? In the past, I heard that a budget prepared for geotechnical can be easily exceeded by implementing geophysics in such projects.
Oh, man.
Question number 25.
Yeah, I mean, the only way to find out what the budget is to ask me. But yeah, you can totally do it for mini or mid-size HDDs. Like if you want to know what's underground, and you don't, if you have money to drill many boreholes, you have money to do geophysics. Like I'm cheaper than the drill rig, as it turns out. I would wish that I was not cheaper than the drill rig, but I am cheaper than the drill rig. So it is a trade-off. You might be able to reduce the number of boreholes that you do if you do geophysics. If by mini you mean going from like a sidewalk into somebody's house for those tiny like utility type projects, I've never done one of those, but I don't see why you couldn't use geophysics for those kinds of things. But certainly it's applicable for those. We can just tighten up the electrode spacing, tighten up the geophone spacing, and increase resolution and decrease the depth of investigation for those smaller crossings.
Max, there are actually a few questions about voids. I think you mentioned that you can use ERT for that. What are some other methods that you can use to identify potential voids?
Yeah, it depends on how deep the void is. Possible you can map out voids with radar, ground penetrating radar. It's possible you can map it out with, there's a seismic processing technique called MASW, or multi-channel analysis of surface waves, that gets you the shear velocity of the material. And voids have effectively zero shear strength versus the surrounding material. So it's a different seismic technique for mapping voids. Depending on how deep they are, you might be able to get it with electromagnetic techniques or gravity techniques. But without knowing how big the void is, like if we're talking like coal seam voids, you can possibly see them, or like tiny coal shafts from 100 years ago mines when they used to be like a meter by a meter. You might be able to see those with MASW. If you have might be able to see it with microgravity, but if it's really deep, you're probably not going to see it. It really just depends on the specifics of how deep it is, how big you're expecting it to be. But resistivity, EM, and GPR are probably your best bets, possibly gravity.
Okay, how about large boulders?
So the large boulder itself, if it's just a singular large boulder, which it's probably not a singular erratic, it's likely contained within some other till material. You can see those often with ERT, you'll see these like resistive patches of where you have a whole bunch of coarse grained materials that the boulders are contained within. If it's really, really big, you might see it in a seismic cross section. But if it's like a boulder-y type zone, it's likely going to show up as a layer of like resistive material surrounded by less resistive material that would be clay or something like that around the boreholes or the boulders themselves.
So is the ERT the best way to identify boulders, or is there a different method?
Yeah, ERT is probably your best bet here. Possibly radar if they're shallow enough and they're contained within, say, sand. You might be able to see these boulders, but maybe I would try ERT first. It's probably your quickest bet for that kind of thing.
Okay, 2 more questions. Do you always perform the SRT and ERT together for bedrock characterization for pipeline crossing?
I mean, I do what the people have money to do. I would recommend doing them both together. If you're just trying to pick one and you want to see how that goes, ERT is a bit less labor intensive. You can still pick bedrock if you have some information of where bedrock is. However, if it's like clay on top of mudstone, it's probably not your best bet and you'd want to do seismic instead. So I would recommend you do both. But if you insist on only doing one, ask me based on what you know about the site, and we might be able to give you our best recommendation of which one is the one that we think you should do.
Okay, there is one question about the cost and quantity, so I would ask the Henry to contact Max for that. Last question, will any of these methods show the location of underground utilities?
Yes. So if this utility has cathodic protection and you do ERT, you'll 100% see this zone. It looks like big metal interference. If you're looking to map shallow utilities, like in a regular trench, there is other better locating methods than seismic and ERT. And if you're looking to map out the deeper, like if it's underneath a river and it's tens of meters underneath, you're likely not going to see those with ERT unless there's. So in short, yes, if it's shallow, radar is your best bet, or EM, like locator techniques that they have. They clamp on and they go around with the wand. That's an EM technique. Or if there's cathodic protection, you'll see it in ERT. But these aren't really line locating methods. These are more for mapping geology.
Okay, perfect. Thank you so much, Max. I think that's all the questions we have today. I would like to thank all CUIIC members listed here. If you are interested in joining CUIIC, please visit CUIIC.ca for more information. And thanks again, everyone, for attending today's webinar. And yeah, that's it. Have a great day.
Thanks, everybody, for your time.
Thanks.